I am an economic geologist, which means that I study the processes that concentrate metals in Earth's crust. And as was mentioned, I focus on seafloor massive sulfide deposits like this chimney structure shown here. Many of the deposits that we actually mine on land for copper, lead, and zinc originally formed through the same processes on the ancient seafloor. So it's a really cool opportunity as an economic geologist to go and study an actively forming deposit on the modern seafloor to better understand the processes that were acting in the past. So in ancient terrains, it can be pretty difficult to understand these relationships between geodynamics, submarine volcanism, and ore formation because they're all metamorphosed and deformed. So it can be a little bit difficult to evaluate all of these big picture processes. So we do this on the modern seafloor in the hopes that it leads to a better understanding of how these form, which is the broad field of metallogeny. This requires kind of being a jack of all trades geologist. It means that we look at things like tectonics and structures that we interpret from bathymetry. We use every kind of data available to us, every geophysical data, sampling, igneous petrology, mapping, and then looking at the hydrothermal precipitates themselves and doing a bunch of different analytical techniques. So before I get started, I do want to acknowledge many of my mentors and collaborators. This is not work done by me in isolation, in particular my PhD advisor, Mark Hannington. And as a Canadian, it's not always easy to get to sea because we don't really have ships that go to international waters. So international collaboration and getting to sea and working with many different seafloor scientists from different disciplines is really important. So many of us have seen videos like this. This is from the virtual vents cruise that was from Schmidt Ocean Institute and GeoMar. And the basic geology of how these things form is pretty simple. Basically, we have some sort of intrusion of magma that provides a heat source that drives the circulation of water through the ocean crust. That seawater will start to drop out alkalis and oxygen, which makes it more acidic and become progressively hotter. And at that point, it starts to leach all of the metals out of the ocean crust, and then it'll rise buoyantly through fractures in the seafloor until we hit the cold seawater at or near the seafloor, and then we're going to dump out all those metals. Some of the metals are lost in the hydrothermal fluids, but also you can see from this video with the sampling, these chimneys are absolutely full of metals. We may also have metals being contributed from magmatic volatiles itself, but that's something where there's still considerable debate. So we are really good at finding the active vent sites. Basically, we take our CTDs, our devices that we drag up and down through the water column to detect the chemical and physical changes produced by these active black smoke plumes. It does mean we have to take a ship out there and survey large swaths of the ocean, but we're pretty good at finding even the smallest vent sites by doing this. Once we've found a plume, then we can kind of narrow down the area of venting to maybe about 1 kilometer, and then we can send our autonomous underwater vehicles or our remotely operated underwater vehicles to go and find the vent source. We have found a lot of these all over the planet. More than 340 of them would be considered high temperature, which means that we're actually precipitating metals. And so all of these are shown by these little red dots. And very predictably, these are located along these different kinds of plate boundaries where we have a lot of volcanism and magmatism to drive the hydrothermal convection. So we have many of these along mid-ocean ridges where it's within international waters, and quite a lot in subduction-related environments, which is generally within exclusive economic zones. So in terms of will there ever be mining of these deposits on the seafloor, a lot of exploration focuses on the Western Pacific within exclusive economic zones simply because you just have to deal with the legislation of the individual countries. But there are a lot of exploration contracts in international waters here. So anything with the little S, these are our sulfide deposits. And so we have 6 contracts for massive sulfide deposits along mid-ocean ridges, totaling 60,000 square kilometers. There also is active exploration for ferromanganese nodules in the Western Pacific and also cobalt-rich manganese nodules in the Clarion-Clipperton zone. And all of this is governed by the UN International Seabed Authority. So in total, 1.24 million square kilometers of the seafloor has been staked basically for different kinds of seafloor deposits, but just note that these are not mining contracts, these are exploration contracts. The legislation's not yet in place for mining of these systems, and we'll see what happens in the next years. From an economic perspective, the principal elements in seafloor massive sulfide deposits are iron and sulfur. But the economic elements, the elements that are of interest for mining are copper, lead, and zinc, along with a bunch of other trace elements are precious metals like silver and gold, and different kinds of what we would call high-tech elements. One of the challenges is that these deposits are incredibly heterogeneous. So in this chart down here, we see the values of copper, zinc, gold, and silver from a bunch of different deposits, and you can see that there's a lot of variability, and there's a lot of variability on the deposit scale too. Just chimney to chimney, these are incredibly heterogeneous. I mentioned we've found more than 340 of them based on kind of back of the envelope calculations of heat flow and the unexplored areas that we know about where we would expect to find some deposits. There's probably a few thousand left to be discovered. The size ranges from just a few tons to over 20 million tons, but very few of these are over 2 million tons. So some of the larger ones include Middle Valley, Tag, and Solwara 1. Compared to land-based resources, these things are tiny, very, very small. Here's an example, a Canadian example, Kidd Creek VMS mine. That's an ancient Archean version of this deposit. It's almost 150 million tons. It's the deepest base metal mine on Earth. It's more than 3 kilometers deep, and they still haven't explored the entire extent. For comparison, here is the CN Tower, our tallest tower in Toronto. And looking at the footprint of the Solwara 1 deposit in Papua New Guinea that Nautilus Minerals once upon a time wanted to mine, it's really very difficult to know why our modern deposits are so small in comparison. So there's a couple of reasons for that. It could be that tectonic processes are operating on a fundamentally different way today compared to, say, the Archean, where the Earth was much hotter. A big reason is likely that we're only seeing the metals that reach the seafloor, so we're missing everything in the subsurface. Drilling is very, very difficult, so we actually don't know the extent of the deposits that we have. Very few of them on the seafloor have very well-constrained resource potential. And the third thing is that we're only finding the active systems. So we're not actually finding most of what could be out there because we haven't been able to systematically survey for inactive deposits. Now, the biggest problem with mining the seafloor, which is basically the environmental risk associated with it. So there's these really unique chemosynthetic communities, and there's a very large push from the international scientific community to protect these active vent sites in particular from deep sea mining. So I guess this is the first goal. This is the goal of my overall research program that will be the focus for the rest of my career. It's not a goal that I'm going to answer in the short term, but how do we develop exploration criteria, not just to find large deposits, but large inactive deposits that could hypothetically have lower environmental risk. So if these different companies are going to push for mining of the seafloor, then maybe we can offer a better alternative. In addition to that, we actually don't know that much about these inactive deposits. We don't know what kinds of communities are still living on them, or how quickly they weather at the seafloor, how they're preserved on the seafloor. So we also want to find inactive deposits just to better understand these systems in general. So it's not just about finding deposits that are easier to mine, it's about developing a more robust understanding of them. So the second really big picture goal of my work is to use the knowledge from these seafloor deposits to better understand the deposits that we are mining on land, and maybe to explore for new ones on land. So this is the classic cartoon model of the TEG deposit, which is arguably the best studied seafloor massive sulfide deposit because it has been drilled. And if you ever go to any industry talk on VMS deposits, they're going to make the comparison to TEG. However, TEG forms along a mid-ocean ridge, and mid-ocean ridges are not preserved in the geologic record. So it's not a very good comparison for most ancient deposits. Instead, we want to focus on deposits that are formed in these subduction-related environments. So those that form along arcs and back arc basins, because these are the deposits that are actually preserved in our ancient record. So whenever we think of a subduction zone, this is kind of the cartoon model that we have in our head. We have our subducting slab, we have our trench, we have our region of flux melting forming our volcanic arc, and then we have this back arc spreading that looks like a very simplified mid-ocean ridge. A lot of studies of subduction zones focus on the dynamics of the subducting slab, but my interest is in the upper plate, so what's going on up here. So in order to form a large deposit, you basically need two things. You need a heat source, so basically an area of very long-lived focused magmatism, and you need a lot of permeability. You need those structural pathways for the magmas and fluids to actually reach the seafloor. So what kinds of conditions on the upper plate can actually lead to that? So rather than this simple cartoon model, let's just take a quick look at a bunch of different subduction zones. So this is some topography or bathymetry of different subduction zones globally. This is just from Geologic Map app. And we can start to see that these actually look pretty complex. Just the geometry of these, we can see that we have going from relatively straight subduction zones to very curved margins. And we see that in a lot of different places, especially in northern Tonga-Kermadec arc. Basically, we move from subduction to transform motion. We have some very big bends in different trenches all over the place. Another thing that we can see is a very common aspect of subduction zones are subduction zone collisions with different kinds of ridges and plateaus. We can see this here where we have basically two large plateaus that have collided with the Isobonan Marianas and basically pinned the top and bottom of the Marianas. We can see chains. This is the Louisville Seamount chain that have collided and are progressively getting subducted. We also see in areas things like the Ontong Java Plateau have collided, and basically if it's a really big plateau, then it's too big to subduct and it clogs up the entire subduction zone. On top of that, other complexities include variable rates of subduction, variable ages of the subducting crust, variable slab dips, and very often we see also multiple episodes of back arc opening where we form one back arc and then the arc will start to rift again. And we'll see that in a couple of different places. So there's potential for inheriting structures or rifting on a really structurally complex plate. On top of that, we have things like, if we're just looking at the back arc, variable proximity to the arc itself, where we can start to supply some of our arc magmas to the back arc. So these are not simple systems. And my main take home for this whole talk is that the geometry and tectonic evolution of each of these subduction zones is really complex, related to all these factors that I just mentioned. So now, how do we make sense of all of this? Basically, we want to know what kinds of tectonic complexities can cause long-lived focused magmatism and these deep penetrating faults and other structures that can promote the formation of large deposits. So basically what we need to do is to better understand the geodynamic evolution of each of these subduction zones and start to better understand all of these factors together. So this all leads to our overriding hypothesis that metal endowment is very closely linked to the dynamics of the ocean floor. So again, my focus is mainly on the Western Pacific. In this talk, I'll be focusing on back arc basins, which account for about 1/3 of the known seafloor massive sulfide deposits. And again, these are our analogs for our ancient deposits. So we're going to just look at one subduction zone, the New Hebrides, which consists of Vanuatu and the southern bit of the Solomon Islands. And so we're just going to address the very broad question of how has the geodynamic evolution of this subduction zone influenced magmatism and massive sulfide formation in the back arc. This is an interesting area because it contains some of the youngest back arc rifts on Earth. So the really basic evolution of this area, I'll just cover very briefly. Originally, the Pacific plate was subducting beneath the Australian plate along this trench here, the Vitiaz Trench, until we had the collision of the Ontong-Java Plateau and the Melanesian Border Plateau about 12 million years ago. That basically clogged up the entire subduction zone. And subduction reversed. So all of a sudden, the Australian plate began subducting beneath the Pacific plate. Really shortly after that subduction polarity reversal, we had the opening of the North Fiji Basin. So this part of the subduction zone started to roll back. So the North Fiji Basin, it opened like two saloon doors, the double saloon doors. So that's why we have the rotation of Fiji and also the rotation of this New Hebrides block. So we had about 2 to 3 million years ago, another collision, this time right here with the D'Entrecasteaux Ridge in the central part of this arc. And so that's resulted in shortening and thickening in the central section, whereas we have continued fast convergence rates in the north and south, continued rollback and extension in the back arc area. So this has basically segmented the entire arc into the north, central, and southern areas. And so I'm going to first talk about what's happening in the south, the Coriolis troughs. So these are very simple back arc rifts. They're a series of Anekalon grabens. They're quite deep, up to over 3 kilometers deep, more than, well, just under 100 kilometers in length. They're 25 to 45 kilometers wide, and they're quite close to the arc front. That's about 50 kilometers from the arc front to the back arc. So this is really what we imagine when we think of a young back arc rift. These also progressively young in age from south to north. So the first thing we visited here in 2013, I want to say. And the first thing that stood out to us is what's happening in the youngest rift, in the Vate Trough. So I'm just going to zoom in on this area here. So this is the bathymetry of the Vate Trough. And the first thing that we notice is that there is a giant shield volcano that spans the width of the entire graben. So the first question is, why is there a huge volcano here? This is a young back arc rift. We consider these to be magma deficient, which means the rate of subsidence exceeds the rate of magmatic input. These kinds of volcanoes we see along mid-ocean ridges where we have intersections with hotspots like axial seamount. We absolutely did not expect to see this in the young back arc rift. So there's also, you can see a large caldera. So this is called the Nifania volcano. And the caldera is similar in size to other shield volcanoes that we find on land-based settings. So the question is, why is this volcano here? And that summarizes basically my entire research program. Why are big volcanoes, big focused magmatism in an area of extension? What are the tectonic reasons for their formation? Why is that there? So in order to understand this question here, first we need to be able to characterize the geology of the seafloor and use some different tools at our disposal as geologists. So how do we start to do this? So we need to be able to identify all the volcanic, sedimentary, and structural features, especially the structural features, areas of long-lived focused magmatism, and these crustal scale faults that are exploited by hydrothermal fluids. So we do have a really important tool that we use. Here is the tool. It's geologic mapping. This is actually a geologic map of Mars. We've never been to Mars, and yet we can map Mars. So this is an approach developed by planetary scientists called remote-predictive geologic mapping. It's basically our best guess. So we can adapt this approach that's used on other planetary bodies, like we now have maps of Pluto and Pluto's moon Charon, but we don't have a map of our entire seafloor at any kind of reasonable resolution. But we can do that. And that's what we have, my collaborators and I have been working on for the last 5 or 6 years. So our main tool is our bathymetry. So our bathymetry we can process in different ways. We can use traditional hill shading, or what we use more commonly is terrain texture shading to kind of eliminate the directional light source. We can look at different parameters like the slope of the seafloor and the rugosity of the seafloor, and we can use acoustic backscatter to interpret where we have hard substrates like young lava flows, because our acoustic signal return will be strong, whereas if our acoustic signal return is weak, then it's attenuated by sediments. So we can basically look at the different fabrics of the seafloor and use that to develop a geologic legend that then turns into our geologic map. So this is the kind of mapping that we can do basically at the segment scale or the basin scale. And here's what it looks like for the Vate Trough. So this is our terrain texture shaded bathymetry, nice grayscale, and you can see that it's very beautifully processed using this terrain texture shading technique. You can get a lot of detail out of it. And here is the first ever geologic map that we produced. So on the basin walls, we have old arc crust that is exposed, ranging from hummocky to faulted to sedimented, and some areas of deeper sediment. The Nifania volcano is in pink, and then different kinds of lava flows are shown on the basin floors. So we have our different rift zones with our hummocky flows and a couple of very large lava plains with some huge collapse features. And we can determine the relative ages of these by onlapping and cross-cutting relationships. And a lot of this was also informed by an old glorious side scan sonar survey. So we can also start to incorporate different kinds of data sets. And then we follow this up with ROV dives to do ground truthing. So looking at the morphologies of each of these in each of the different dive areas and collecting samples. The other thing we see are a bunch of tiny little volcanoes all over the place, and these white features are fissures or dikes that have reached the seafloor. And we can see that that cuts across one lava plain, but not the other, so maybe this one is a little bit younger. But more important than all of that are the abundant structures that we see. So in this case, we have abundant normal faults because of the extension, and we can look at the orientation of the structures. So in the northern part of the basin, they're approximately parallel to the direction of opening. But as we get closer and closer to the Nifania volcano, we see that there is a counterclockwise rotation in the orientation of the faults, and especially the dikes on the volcano. So this tells us that the entire area around here is under left lateral transtension. So the next step is to relate that to the bigger picture. So again, here is kind of a cartoon overview. The green areas are our subaerial volcanoes. Here's our trench and our subduction rates, and in pink, these are our back arc troughs, and the Nifania volcano is right here. And then the contours are just the depth to the top of this slab. So basically, the reason we have left lateral transtension is because once we had this collision with the D'Entrecasteaux Ridge, we essentially have this rotation of the southern segment that is inducing the left lateral transtension in the back arc. So what happens is these oblique shears open up and form the large large conduits in the rifted arc, focusing magma at the Nifania shield volcano. And the reason why this is really happening in the Vate Trough is because it's the youngest trough and has had its almost entire life affected by this collision with the D'Entrecasteaux Ridge. So all of this tells us that there's a direct link between the style of volcanism at Nifania and the upper plate stresses related to the fragmentation of the New Hebrides arc and this asymmetric rollback of the subducting plate. The other thing we can link this to is things like the composition of the volcano. So because we have these voluminous eruptions associated with really rapid melt extraction, we get some very unusual alkalic compositions. So this is really low degrees of partial melts. So basically these low degrees of partial melts have been really efficiently extracted in this process. So what does that mean for hydrothermalism? Let's just zoom into the caldera. Here are some of the lava morphologies. We have pillow flows, lobate flows, sheet flows, and a lot of these sheet flows were super glassy and unsedimented and looked like they had erupted yesterday on the seafloor. We also have some collapse pits. We don't have very good pictures of them, but basically this is where we have our jumbled sheet flows, and then there's a big space underneath, a big pit. So this is actually a lava lake, so our lava ponded and then drained away. So we can also make maps of the distribution of these different morphologies. So it's better when we have higher resolution bathymetry than we have here, but this is based on ROV dive observations. So we can see we have our main fissure with at least 2 ages of lobate flows shown in blue and some pillow mounds. And then in green, these are all of our sheet flows that are ponding against the northern side of this crater. And we do have hydrothermal venting in one area. So zooming in here, again, this is the kind of map that we can make if we have a bunch of ROV dives. It's kind of like doing geologic mapping at nighttime with a flashlight. It's not the easiest thing to do. So again, we see that we have areas where there's diffuse venting shown in red and areas of old inactive chimneys and some iron oxides, and then we have some areas where we have active chimneys. So the diffuse venting, it's basically hot milky fluids emanating from our interpillow spaces, and our chimney structures look like this. We have chimneys that reach 368 degrees Celsius, which is actually boiling. This tiny little flame-like structure is boiling. So the hottest temperatures that had been measured in the Western Pacific. And basically these are venting almost pure vapor phase. The really interesting thing is that if we look at where these chimneys are forming, where we have this focused venting, it's right kind of at the transition between pillow mounds and other lava flows. So our fluids are really being focused along these permeability contrasts in different kinds of lava facies. The other thing that we see are these are quite tall chimneys, and if we look around the base of all of them, they're basically growing right on the lava. There's no talus, and it's a very seismically active area. So you would expect, like in many areas, that these chimneys will grow and then break off and continue to grow and build up a mound and be surrounded by some sort of sulfide talus, but we don't see that at all. So this tells us that basically these are very young. So our interpretation is that the effusive eruptions that produce these very young-looking sheet flows release massive amounts of hydrothermal fluids over really short time intervals associated with these eruptions. So we call these mega plumes. But what happens after that is that you get really rapid cooling and generally poorly focused discharge. We're only focusing it at these permeability contrasts. So the overall impression is that the venting is very young, probably less than 20 years based on the frequency of large seismic events and just getting organized. And it's very likely that the heat source is just the intrusion of different dikes rather than some larger system. So we probably don't really have sustained hydrothermal circulation at depth. So this isn't really an area where we would expect there to be a very large deposit. So again, we're really limited in our understanding here of just what we see in an active system. But if we could explore around the caldera margins, it's more likely we could find one of those inactive deposits where we have the caldera rim faults that are more deeply penetrating. However, we can still basically link the processes of focused volcanism in an extensional environment and use that to really understand ore deposits. So the take-home messages just with this area is that there is a very direct link between the geodynamic evolution and the siting and style of magmatic hydrothermal activity. We can open structural conduits during terrain collisions to promote rapid extraction and focusing of melt, to form a shield volcano in a nascent back arc, something we did not expect. That results in rapid effusion of low viscosity sheet flows with lots of heat loss and short-lived high temperature venting. So we can also think of this in terms of the different stages of caldera collapse. So right now, the caldera is at a stage of resurgence. So that means that all of the activity is focused in the central part of the crater. Whereas if we have an initial stage related to caldera collapse, that's more likely to form the larger deposits around the caldera margins. And there's a really great paper by John Stix et al. In 2003 that walks through that. So now I'm going to move on and go to the northern back arc. These are the Jean-Charcot troughs. The Jean-Charcot troughs, here's just satellite altimetry. We don't have good bathymetry in this area, so the resolution's not very good. And the troughs are shown by this gray hatched pattern. So the immediate thing that we see when we start to compare what's happening in the south and the Coriolis troughs to here is that these look very different. They're really irregular. They're widely distributed over about 120 kilometers. They don't look like simple grabens. And so the question is, how do we account for this really irregular and widely spaced distribution? So we can look at whatever data that we have. In this case, we have some pretty crappy magnetic data available. And here we have our magnetic lineations that we see are extending from the North Fiji Basin and extending right through that back arc. We also see some structures, like here's the Tikapia fracture zone. This is a paleo spreading center that formed during the opening of the North Fiji Basin. And that also, if we trace it into the back arc, we see that there's this area of a bathymetric high. So this is telling us that that this is likely a very large lithospheric scale structure that magmas in the back arc are just exploiting. And that's kind of bisecting the grabens in the back arc with this bathymetric high. So all of this tells us that this irregular morphology is likely related to the fact that we're not just rifting a simple arc. We are rifting an upper plate that has a lot of these pre-existing structures and is very structurally complex. So basically the fact that we opened the North Fiji Basin first and then rifted this basin has played a big role in the evolution of this part of the back arc. And it gets a bit more complex. So when we had our double saloon door basin opening, this produced both arc parallel and arc perpendicular rifts. This is from Martin in 2013. But then again, we had this collision with this D'Entrecasteaux Ridge, this buoyant plateau. So in the south, we already looked at the implications of that, but along this northern block, it's basically caused the rotation of the block to switch directions. So from GPS measurements, the hinge point is about here. So close to this hinge point, we have more sedimentation, and as we move further away, there's kind of more torque, so we have more active extension and deeper basins in the northern part. So it could be that this reversed block rotation has actually enhanced extension in this northern part of the Jean-Charcot troughs. So it's very dynamic and very complex, and also this is one of the least studied back arcs in the world, and we need some more cruises to collect some better data to make more robust interpretations. But again, we are looking as economic geologists to understand where magma supply is focused. So we zoom in to this middle part right here, where we have this bathymetric high tracing the extent of this Tikopia fracture zone. So here's some ship bathymetry. Along the arc, we can see that we have an old rifted arc volcano and lots of normal faults. And as soon as we get into the back arc, we still see lots of north-south trending structures. So this is that very strong east-west extension producing these structures. But all of these are different volcanic fissures and cone rows. We also have a large volcano called Starfish right here. So basically, all of these extensional structures are being exploited by magmas, which is great if we're looking to form a deposit. So we do have an area of active venting on the flank of this Starfish volcano. Here's some higher resolution data. This is 50 centimeter resolution bathymetry collected by a company called Neptune Minerals. We see a couple of larger volcanic cones. And then we see a series of smaller cinder cones. And the morphology and alignment of these cinder cones is basically the same as what we would expect on land. Here's the Laki cinder cone row in Iceland. So this is our submarine equivalent. So we are at over 1,000 meters water depth. And yes, we can get explosive volcanism at this water depth. The only difference is that the diameters of these cones are a little bit smaller than the diameters of these cones because our fragments don't disperse as much. So again, now we can start to look at the geology. So this is again from ROV dives, huge amount of ROV dives and a lot of sampling. So our composite cones have either dacite flows or bimodal dacite and basaltic andesite, and our cinder cones are all basaltic andesite. And then all of the bright pink and purple, those are different chimneys and mounds that are active or inactive, and there's over 900 individual chimneys in this area that coalesce into these mounds. So the footprint of just the chimneys and mounds is almost 77,000 square meters. And these are actually partially buried. So all of the brown here is sediment. It's volcaniclastic fallout from a nearby eruption. So a lot of these mounds are partially buried, and that sediment has been indurated with hydrothermal activity. And then just in 3 dimensions, looking at the relationship of where these mounds are in relation to these different cones. They're forming at the top of the cones, in the middle of the little craters, on the flanks of them, but also on the sea floor, just not associated with any kind of volcanic activity. We can also do dating of our hydrothermal barite, radium-226 dating of barite. This was work done in collaboration with John Jameson at Memorial University of Newfoundland. And we have essentially continuous activity over the last 5,500 years. So this includes samples from our ROV grab samples and also some deeper drill hole samples. So if you recall anything about volcanic activity, we know that these cinder cones are considered monogenic. That means they form in one event from days to weeks to months, but certainly not over thousands of years. So the volcanic activity that formed the cinder cone row is not related to the formation of the vents here. The hydrothermal fluids are just exploiting the same structural pathways along this fissure system. So I mentioned that we also have drilling. And here's just some pictures from our drill core. This is from a lander type drill. So we drill, so this was all work done by Neptune Minerals again. And so the drilling is generally about 10 meters below the seafloor, up to 25 was the deepest drill hole. And you see a lot of different volcanic clastic facies, everything that you would expect in the cinder cone row, highly altered, so that's why they're so light color and green, and very strongly cemented by anhydrite. So the important thing is, even though the volcanism at the seafloor is not temporally related to the formation of the vents. This is telling us something about the substrate that our fluids are moving through. And these kinds of host rocks are really permeable. So what we get is a lot of seawater mixing near the seafloor. So it's actually kind of incredible that we have focused venting forming chimneys and mounds in an area that's so permeable with so much seawater mixing. So actually we found that so much of this area was underlain by anhydrite. So the precipitation of anhydrite at temperatures over 150 degrees allowed this fluid focusing. So this means that we're reaching very high temperatures within just a few meters of the seafloor. And this is also really important because when we look at ancient deposits, anhydrite has retrograde solubility. So as soon as we drop below this temperature, that anhydrite will dissolve into seawater. So it's kind of rare to have anhydrite preserved in an ancient deposit. So this is a process that's probably been overlooked in quite a lot of ancient settings. The only evidence we would have is different kinds of alteration assemblages that would form at the same temperatures. So just looking at a couple of quick cross sections of some of the drill holes in the north, we have this small crater. At the surface, we have our chimneys overlain by some sediment, and underneath that, there's kind of a discontinuous layer of chimney talus, and everything below that is our volcanic clastic rocks. And we can look at the different minerals in the alteration assemblages. So we have illite smectite plus pyrite, illite smectite plus camosite, and then camosite and krentzite. So this is corresponding with a downward increase in alteration mineral temperatures. We can also calculate the temperatures. We can calculate it two ways. One way from fluid inclusions in our anhydrite veins, and also looking at oxygen isotopes when we have monomineralic clays. And we can see in some areas that we have gradients of 80 degrees in just a couple meters. And then we have another example down here where we actually have a couple of different paleo seafloor horizons, which is absolutely expected. We expect that some parts of the system will be active and then inactive kind of episodically. And again, we have these different alteration assemblages. And these are really what we would call stratiform alteration assemblages, exactly what we would see in an ancient system. So we have a lot of seafloor mixing, very high temperatures close to the seafloor, and a lot of lateral fluid movement, all related to the fact that we have venting associated with this style of volcanism. And this style of volcanism is exactly what we see in extensional terrains. So again, there's a direct link between the geodynamic evolution and the siting and style of hydrothermal activity. These young irregular grabens are formed by rifting a structurally complex upper plate, including a pre-existing paleo spreading center. And the more work we do in different subduction zones, the more it's clear that arc orthogonal faults are absolutely key to enhancing magmatism in the back arc. So again, this is on the seafloor, an area of enhanced magmatism that, coupled with this very extensional environment, forms these kinds of fissure systems. And then our fluids can exploit the fissure systems, producing this kind of massive sulfide deposit. So the question is, how can we start to use this information to A, find inactive sites, and then B, relate this to ancient successions. So the first thing is that now, if we understand the evolution of any given subduction zone, we can start to pick out areas where we have the features that we need, the ingredients that we need to form a deposit, and go and search there. This is an area, or this is an approach that we call mineral prospectivity mapping. And then in ancient successions, once we identify features like these large arc orthogonal faults on the modern seafloor, we can adapt our exploration approaches on land to start looking for these. Once a structure, always a structure. So normally our surveys are going across arc successions, but then we're not going to see these faults. We need to do along arc geophysical surveys. So just the final comments here, just looking at this one single subduction zone, these upper plate stresses can result in dramatic variability in basin morphology, magma supply, and hydrothermal activity right from the earliest stages of arc rifting, but they do continue through when we get to more mature seafloor spreading. We can link features to specific tectonic events or specific complexities like pre-existing structures and ridge collisions, and this can result in distinct changes just along a single subduction zone. So we really need a better understanding of these processes to develop those exploration criteria and move forward. So that's all I have to say, and I welcome any questions.